Hi class, this is going to be a quick example on the lab and how you should be able to generate your stress strain data and get the elastic modulus, the yield strength, ultimate tensile strength, percent elongation or ductility, our toughness, and the resilience, all from our data. Now, this is a clarification because the data that we get, if we're just to plot it straight away, is not stress strain data. It's basically given to us in column 1 with time, column 2 in extension, or column C load, and then column D in tensile strain, and that's a percent strain read out from our extensometer. So what we need to do is we need to get this back into the correct formula, or maybe not back into, but make it into the right form. So the way to do this is to plot it as a stress versus strain curve. Now remember that stress is equal to force over the cross-sectional area. And we have a force in newtons, and if you took your samples data in millimeters, you might have a millimeter squared. That's equal to pascals times 10 to the 6, or 1 megapascal, which is typically actually the units that you'll see a stress strain curve plotted in. So if you divide your force by your area, you'll get megapascals. The next thing is we need strain, and we don't need percent strain, we need that in millimeters per millimeter. Now we don't have to do any L naught minus Li over L naught because our strain gauge already captures that data for us. So all we have to do is convert a percent strain to millimeters per millimeter, and that's simply done by dividing your percent strain by 100, and that'll go back into the unitless millimeters per millimeter. So this curve that you're plotting should be millimeters per millimeter, should be unitless. And what that will tell us then right here, 1 is the elastic modulus, and that's given as the slope of the linear region. So this equation should look like, well, let's just say for general equation of a line, it's y equals mx plus b, right? Well, ours is stress is being plotted on the y-axis. M is the slope. In this case, that's our Young's modulus, E. And then X is our strain, and then plus 0, because we're saying that in theory, if we have no strain on our sample, there should be no stress. So stress is equal to Young's modulus times the strain for our linear region. So what we can do is if we plot this, we can get the strain as the slope of the initial linear region. Now, that's actually a little trickier to do than you might think because it's difficult. How do you define what the linear region is? So I'll go through that. And then the next part is to do an offset curve of 0.2% or 0.002 strain and plot that same line, so the slope of E, and find that intercept. So the way we do that is we need to basically find E first and then force a new line, an offset line, to go through 0.2. So if I wanted to do that, what I know at 0.2, you know your stress should be equal to 0. So you can solve for what the sort of implied y-intercept should be for your offset curve. So we need to solve for that. So the way you do that is say 0 is equal to E times 0.002 plus B. And then you could say that B is equal to negative E times 0.002. And then what you'll do is you'll just recalculate what the curve should be. We know the equation now is stress offset is equal to Young's modulus times strain plus B offset. So that's how you can do your offset curve, and then the intercept, can't spell for the life of me. Sorry, the intercept is equal to your yield stress, or sigma ys. That's the point we need to find. That's probably the hardest point to find on this curve. So I actually hate using Excel. I'd much rather do this in MATLAB, but since I don't expect you to have taken MATLAB, since it's not a prereq for our course, I'll go through how you might do that. So here I've set up an Excel spreadsheet that will do it automatically for me, and I'll take you through how I did that. So the first step is to go to my raw data, and I'm going to copy all of my extension, my load, and my strain data, and then you can shift control press down so I get all of it. Look at that, it's 4,141 data points. So it's a lot of data points. And then I'll go in here and just paste that in to my thing. And so what I first step to do is to convert my percent strain into just a unitless strain. So that is, I just take the cell of the strain and divide it by 100. And if you were to double click the little cross at the bottom, that'll take it all the way down. Now the stress is calculated simply dividing by the force by the area. And I have my average specimen width times my average specimen thickness. So you should have over here thickness and width, and you should have 3 measurements for each. And then what I did is I take an average of those numbers. So that can give me my gauge area. Remember, it's the area of a rectangle, so it's just thickness times the width. So that will calculate your stress. And you can plot it out, and it should look something like this. And to really understand what's going on for the yield stress, I'm going to zoom in to this sort of initial portion. And so here's a plot of that initial portion. And you can see we've got kind of a little hump, and pretty much everybody's data did this, where we're taking out slack from the specimen grip fixture, and we can't really trust this portion of the data. So what I'm going to do is, for everybody, we'll say this is our rule. It's at 0.005, or sorry, 0.005 strain. We're going to throw out the data to the left of it, or disregard it in the calculation of our Young's modulus. So what I set up here, so I can parameterize it, is a lower data limit. That way I can play with this number and I don't have to go back in. So I've got my lower data limit, and then I also got my offset, because sometimes your offset limit is different for plastics. So if I want to reuse this same spreadsheet for plastics, I could just change my offset limit. Okay. And so this is where it's kind of a pain in the neck to do this in Excel. But what I said is my, let me recalculate and sort of take part of this as my linear data. And so the way I can sort of ignore the data that is below the strain that I think I should actually capture, I said if D10, so if the strain reading is less than N, and it's important for $ too, because that'll keep this cell fixed as I drag this formula down. And so if it is less than, or if it is greater than that, then I'm going to go ahead and keep that stress value. So I'm saying, okay, well then the stress will be this value, and if it's not, then it's going to be 0. So that's how I get that. And then what I'm going to do is I am going to take the tangent modulus. Now let's see, what is a tangent modulus? And it's really just the slope between any 2 points. So, for example, I could have this point and the point right next to it. I can get the tangent modulus is basically that slope is y2 minus y1 over x2 minus x1. And to calculate the tangent modulus, our data, we're taking a data capture every tenth of a second. So if you go back to our raw data, I'll show you here. So in this raw data, I'm capturing every tenth of a second. So to kind of smooth out my fast data capture, I will take my tangent modulus as being the slope for every 1 second of data capture. And how I do that, and it's kind of backwards with Excel, that's why it's is I'm basically saying, well, if my data is below the strain threshold for my data that I want to keep, then I'm not going to count it. I'm just going to say it's equal to 0. But if it is greater than that, what I'm going to do is take the slope of the next 10 adjacent data points. So that's basically the slope of 1 second's worth of data. And that should smooth it out for me. So I drag that all the way down to the bottom. And then you'll see here is it is going to switch over when my strain hits 0.0005 millimeters per millimeter. Then I'm going to start capturing my tangent modulus. And you'll see these values are pretty different. They're not all the same. So what I'm going to do is for my reported modulus of elasticity, I'm going to take the maximum slope. And the reason you do that is because it's the stiffest the material is. That initial material response really is the true material response. The further we go out along the curve, the more the sample is starting to yield, and it's not exactly the linear region of the curve. So we will take the maximum. So that's how I do that. And then I already have my yield strength. So how did I do that? Well, let's show you. So I'm going to go to this chart, and I have a couple sets of data that I've hidden from you. What I plotted here was a 0.2% offset, and then that's my intercept, so that's my yield strength. And then I plotted also the initial sort of proportional part of my data. This is a extrapolated proportional part. And the reason I do that is to double check that the Young's modulus I get actually looks like it's coming from my data. If it's way this way or way that way, then it's probably not correct. So this actually looks pretty good. And so I'll take you through how I do that. So the 0.2% offset strain is one thing I'm going to do is I'm going to take my strain in millimeters per millimeter, and I'm just going to add to every single data point the offset. So that effectively shifts those data points to the right. So I'm basically take this data point, and it's important that you do the $sign. I am shifting it by 0.002. So I do that to all of the strain. And then I calculate my offset stress. And this is where I have to go back to my derived equation for a line, because I have to calculate my offset stress. And so that is my Young's modulus times the strain, but then I have to have the plus the B, and this minus N4, which is my offset 0 point, and then my Young's modulus. So this is my back calculated B intercept for the offset curve. So now I can basically plot, I can calculate that for every data point, and that is here. So I'll look at that. What I've done is I've plotted the offset strain and now calculated offset stress. And to find the intercept, And if you look in here, it's right a little bit above 400, but we're not going to leave it to judgment. We're going to let our Excel formula find it for us. So what I do is I make a column called offset delta. And I'll take you back into here and show you how I were to calculate that. The way I can find this intercept is basically I know at some point on my curve that the data I captured, so my data stress and my data strain value will be equal to or very close to equal to the offset curve. So at each point, I can subtract them, and you'll notice they're getting smaller, and then they start to get bigger. So at some point, that should go to 0. And when it goes to 0, that value would correspond to your yield stress. You know, some of these formulas up in Excel, not a very friendly environment to do things formula based, but so here I basically subtract the stress from, and I'm taking the absolute value from my offset stress. And I have to calculate that actually. So here is E10, which is this value right here, but then I have to calculate the predicted value for my offset curve, because actually right here, the predicted value is going to be somewhere down here below, so it's actually going to predict a negative stress. So the way you do that is just say, okay, well, you take the strain value and you multiply it by your Young's modulus and the intercept that is for your offset curve. So I can do that, and at some point it should go down to 0. So if you look at this, I could scroll all the way down, It's still pretty high, and you're going to probably give yourself a headache to try to find it, which is why I never do. I actually couldn't do it here. So I just do it with it here. And there's basically a way where you can do this match. And I'm going to say, I'm going to take, because it's never actually going to be equal to 0, but I'm going to say this whole set of data, the very minimum value of that, we'll say that that's the closest it came to being 0, the difference between my offset predicted stress and the data stress. And then I'm going to take that index and report the stress value and call that my yield stress. So I'll share that formula, but right here, it does it for me. So, and if you look at 402 megapascals, that's right on. So I don't have to scroll through a bunch of data. I'm just having Excel do it for me. And then my tensile strength, that one's easy. All you have to do is take the max stress that you calculate. So that one is easy. Ductility, that is a trickier one. What you have to do is it's not the last data point that you captured. So what it is, let me go back here, is on this curve, you have to basically do the offset of another curve. So the same way you offsetted the 0.002% off or 0.002 strain offset, you're going to have to do that here. But now instead of knowing that there's a point at 0 stress and 0.002 strain, you know this data point of fracture, and you're going to have to back calculate some new B or new intercept, and then you can now calculate the value of strain when stress is equal to 0. So that's this 0.4 here. So here I calculated that as 13.67%. The final two pieces of data, now it's looking good. We've pretty much got our Excel sheet going. The final two pieces of data that we're going to have to do is the modulus of resilience and the modulus of toughness. And if you go back here, the modulus of resilience is the area under the entire curve, and the toughness is the area underneath the linear portion. So how do you do that? Well, we just take Riemann's sum. All we're going to do is use the rectangle rule to estimate this area, because Excel, I don't actually know how to do it in Excel. Probably be easier with other programs, but that's basically you take two data points, two adjacent data points, and you take the area of that, and then you add them all up. And so basically you take an average height. This is the midpoint rule. So let's say this is sigma 1 and this is sigma 2, and this is stress 1 and this is stress 2. The way you would do that is this little area, using the midpoint rule, and let's just call this AI, is equal to the average, so sigma 1 plus sigma 2, so the average height, so divide that by 2, and then you times that by the delta string, so sigma 2 minus, sorry, epsilon 2 minus epsilon 1. So that would be my individual area, and then I just add those all up. So how did I do that in Excel? So the modulus of resilience here, I have as this. So I basically take the area of two adjacent curves, but I don't count it if the strain value, E11, or sorry, the stress value, I don't count it if it's less than my yield strength. Sorry, yeah. So that's how I can basically calculate this and keep it as the modulus of resilience as the data points that are to the right of my stress, yield stress. So if E11, my calculated stress, is less than the yield stress, which I calculated up here, then I will do the basically midpoint rule to calculate that little incremental area. And if not, it's 0. And so what that will be is I'll have a whole bunch of little area chunks, and at some point when I pass up the yield strength, it'll be 0. And the reason I want that is because I don't want to know where this point is. I just want to add everything up and then not have to worry about finding that. So if I were to add everything up in this column, and you see here's my yield stress, oh, and you can see here is that is the minimum delta right there. So now I can use that to systematically find it without having to scroll down for my data. And then for the total just toughness, I don't have the if statement. I just add up all of those areas. So in this modulus of resilience, I summed this entire column K. And in the toughness, I sum the entire column. And it's in megajoules per meter cubed. So you can look up the unit conversions there. You should make sure that you're doing the right units. Okay, so that's a quick sort of overview of how you would make this or get this data from your raw data. I'm going to go ahead and post a sort of template without the all the calculations because I want you to do that. But if you're stuck, hopefully you can look at this video and it'll help you out from getting stuck. So we need to find this initial portion systematically, and we'll take that as the data above 0.005. I looked at everybody's data and that seems to be about the right value. And then we need to find where that intercepts your data, and you can call that your yield stress.